Hello everyone and welcome to our calculus notes for section 3.3. Today we're talking about increasing and decreasing functions and the first derivative test. So first let's take a look at increasing and decreasing functions. So we know that if a function is increasing, it graphically is going up from left to right. Algebraically we can see here that these y values are getting higher as the x values are getting higher, and that makes our function increasing. Alright, we also know that we can have a function that is constant. So this is just a straight horizontal line here. Graphically, we do get that horizontal line. Algebraically, we say as x increases here, y stays the same. And that is why we call this a constant function. And our last one is decreasing. Okay, graphically, we can see that this function goes down as x moves from left to right. Algebraically, we say as x increases, now your y values are decreasing. And so we call this a decreasing function right here. Okay, so graphically, easy to see, increasing, constant, decreasing. Algebraically, I think we can understand that as well. What we're going to talk about today is how the derivative is being affected during an increasing, constant, and decreasing function. And right here it says if f prime of x is greater than 0 for all the x in a certain interval, then f is increasing on that interval. So here, from a to b, we would say f prime of x is greater than 0. And that's how we know this is increasing. If f prime of x equals 0, then we know the function is constant. So here, we're going to say f prime of x equals 0. And then if f prime of x is less than 0, then we're going to say this is a decreasing function. So if f prime of x is less than 0, now we have a decreasing function on the interval. Now we can also think about something greater than 0 is positive, this equals 0, and then something less than 0 is negative. Okay, so this is our test to determine where a function is increasing or decreasing. So some guidelines for finding these intervals where the function is increasing and decreasing. And we're going to assume that f is continuous on the interval. It says locate the critical numbers of f on a and b and use these numbers to determine our testing intervals. Okay, then we need to determine the sign of the derivative, f prime of x, at one test value in each of these intervals. And then use the derivative test for increasing and decreasing functions. So we're going to test whether it's positive, negative, or 0. So your question is going to say find the open intervals on which the functions are increasing or decreasing. So the first thing we have to do is find the derivative of our function, because we're going to be looking for the critical numbers. So we find our derivative, and this one is 3x squared minus 3x. Okay. After we find the derivative, we have to set this equal to 0 and solve. Okay, so we can divide everything by 3 here. And if we factored this out, we would get 3 times x minus 1. And so here, x equals 0 or 1, and these are our critical numbers. Okay, so that was step number 1. It said locate the critical numbers, and now we want to use these numbers to determine our test intervals. So So basically, we're going to put our critical numbers right here, 0 and 1. And we're going to be looking at intervals around these critical numbers. So basically, to the left of this, we're going to be looking from negative infinity all the way up to 0. Here we're going to be between 0 and 1. And here, from 1 to infinity. Okay, so now we have our testing intervals. And it says, determine the sign of f prime of x at one test value in each of the intervals. Okay, so we need to test some values here in each of these intervals. So here we can try something that's just less than 0, so like -1. And so what we're going to do is actually find f prime of -1. Here we could try f prime, something between 0 and 1. Let's just try 0.5. And here we need something greater than 1, so let's try 2, and let's find f prime of 2. Okay. Now you can just type these into your calculator, and you could write your values here. So f prime of -1, that is 6. F prime of 0.5, that's -0.75. And f prime of 2 is 6. Now we don't really care what the values are other than the sign of the values. So basically, is it positive or is it negative? In this case, it is positive. Here it's negative, and here it's positive. Okay, so what that means is, let's do our conclusion. On this interval right here, our derivative is positive. Therefore, we say this is an increasing on this interval. Okay, and the interval is -infinity to 0, and that is an open interval. Here, the derivative is negative between 0 and 1, and so we say this is a decreasing function on the interval 0 to 1. And here our derivative is positive, so again, this is going to be increasing, and that's our interval from 1 to infinity. Okay, so graphically, what we can know here is that at 0, we have a critical number, and then at 1, we have a critical number. And we can find our f values here at 0. So f of 0 equals, that's got to be 0. And then f of 1, that's going to equal, let's see, 1 cubed minus 3 halves. So that's going to be -1/2. And we could plot those points. So we have 0, 0, and 1, -1/2. Now we know our function is increasing, so it's got to be increasing on this interval here. Okay, and then it's decreasing on this interval, and then increasing on this interval right here. Okay, so increasing, decreasing, and increasing. We have something called a monotonic function, which I just want to define for you. And monotonic means that it's either increasing or decreasing over the entire interval. Okay, so something like x cubed is increasing here. Then as it gets to 0, it kind of slows down, but then it keeps on going here. Okay, so you can see it's increasing on this interval and it's increasing on this interval. So this one right here is monotonic. Now if we look at this graph right here, it's -x² when x is less than 0. Okay, -x² looks something like this, so this is increasing. In the interval between 0 and 1, so from here to here, our function equals 0. So right there, it's constant, and our derivative would be 0. And then x minus 1 squared, when x is greater than 1, it just looks like this. And so that's positive also. Now you can see we have positive and positive here, but because of this interval where the function is constant, we would say this is not monotonic. Let's move on. So here is the actual first derivative test. It says let c be a critical number of a function that is continuous on an open interval containing c. The first derivative test states that if f is differentiable on the interval, except maybe at c, okay, so that kind of sets up our thing. We have critical numbers, it's continuous and differentiable. We're going to say if f prime of x changes from negative to positive at c, then f has a relative minimum at c, f of c. So let's think about what that means. Okay, so we're going to have a critical number here at c, and the derivative is going to change from negative to positive. Okay, so on this side, we know that f prime of x is going to be less than 0. And on this side, f prime of x is going to be greater than 0. Now what do we know f prime of x is at c? Well, we would know f prime of x equals 0 right here. So if we were to graph this, we know this is a decreasing function here. So we know this function is decreasing until we get to c, where it's 0, and then we would know it's increasing afterwards. Okay, so f prime of x is greater than 0, or less than 0, means this is negative and decreasing. And here, on this side, it's positive. So what does that tell us about this point, f of c? Well, we know that c, f of c, is a minimum. Okay, so it's negative to positive, we get a minimum. Now, if f of x changes from positive to negative at c, then we have a maximum. So here, f prime of x is greater than 0, and then at c it switches over to f prime of x is less than 0. So that means we have an increasing function. It hits c and it's 0, and then we have a decreasing function. Okay, so this would be positive, negative. Here's our critical number, and that would make this a maximum. Now, if f prime of x is positive on both sides of c, or negative on both sides of c, then f of c is neither a relative minimum nor a relative maximum. So let's draw both of these situations here. So here's a c, and let's just say f prime of x is positive, and here on this side of c, f prime of x is also positive. So let's think about what that means. It means we have an increasing function, and then at c it's going to equal 0, and then it has to be increasing again. So here we had a positive, here's our critical number, cf of c, but then it's positive again. So notice this is not a maximum or a minimum. The same thing happens if at c the derivative is negative and then is negative on the other side of c as well. So here we have a decreasing function. We hit 0 at c, and then it's decreasing again. So here the derivative is negative. Here's our critical number, cf of c, and here it's negative again. And here we don't get mins or maxes. Okay, so let's go ahead and find the relative extrema of this function, and we are going to use our first derivative test. So the first thing we have to do is find those critical numbers. So here we get 1/2 minus cosine x. So we need to find where this equals 0. So where does cosine x equal 1/2? Okay, let's take a look at our interval on 0 to 2 pi. So again, that's just our unit circle. So cosine x equals 1/2 at pi over 3 and 5 pi over 3. So what happens here is this becomes the intervals we have to check. So we're going to put pi over 3 right here and 5 pi over 3 here. All right, and writing out our interval, we'll just say 0 is our left endpoint. Is less than x is less than pi over 3. Here the interval is pi over 3 to 5 pi over 3. And here our interval is 5 pi over 3 to 2 pi. Okay, so we need some test values between 0 and pi over 3. So we could try something like pi over 4. Okay, we need a test value between pi over 3 and 5 pi over 3. Well, pi is right in the middle there. And then between 5 pi over 3 and 2 pi, so let's try, well, this right here would be 8 pi over 4. So let's try 7 pi over 4. And that is bigger than 5/3. Okay, so it's just going to be a little tricky. You got to make sure you find an interval right in there. Okay, now you can go and plug these into your calculator, and really what we're looking for is the sign that results here. So if you type this into your calculator, into the derivative here, 1/2 minus cosine x, you actually get about negative 0.2. If we plug pi in, we get about 5.8. And if we plug 7 pi over 4 in, we get negative 0.2 again. So really the only thing that really matters here though is the sign of f prime of x. So here the sign is negative, here the sign is positive, here the sign is negative. So what's our conclusion? Well, the conclusion is on this interval we know the function is decreasing. On this interval the function is increasing, and on this interval the function is decreasing. So what does that tell us is happening at our critical values right here? Well, again, the first derivative test says if we go from decreasing to increasing, this has to be a relative minimum. And if we go from increasing to decreasing at a critical number, remember it looks like this, that makes this a relative maximum. Okay, so the minimum, we know the x value is pi over 3, and the maximum, we know the x value is 5 pi over 3. Now, to go ahead and find our answers, let's just go ahead and get an approximation. You're going to plug them back into this original function. Okay, so to find our minimum, we need to find the point pi over 3, comma, f of pi over 3. Okay, and so f of pi over 3 is going to be 1/2 times pi over 3 minus sine pi over 3. And you can just plug this into your calculator, and we get about negative 0.34. Okay, so our relative min here at negative 0.34. And then for our maximum, we need to find 5 pi over 3, comma, f of 5 pi over 3. So we get 1/2 of 5 pi over 3 minus sine of 5 pi over 3. And this gives us about 3.48. Okay, so let's go ahead and sketch this here. We want to think about if we plugged 0 into this, that would come up with 0. So we have open circle on 0. We know we have a minimum at pi over 3, comma, negative 0.34, which is about right here. We know we have a maximum at 5 pi over 3 and 3.48. So 5 pi over 3 is here, and 3.48 is about right there. Okay, and if we plugged 2 pi into our function, the end of our interval, we would get, well, let's see, half of 2 pi is just pi, and then sine of 2 pi is also 0. So pi minus 0 is pi, and so that's right there at about 3.14. And this is going to be an open circle there. So if we think about it, it's decreasing on this interval. We have a relative min. It's increasing on this interval. Then we have a relative max. And then it's decreasing on this interval right here. Okay, so you can see it was minus, plus, minus. And so we do get a minimum here and a maximum right up here. All right, let's give another one of these a try. Okay, so I want you to just work this problem along with me. First thing we need to do is find our derivative. Okay, and what rule do we use right here? That's got to be the chain rule. Okay, and let's simplify this. Okay, so now we need to find where this equals 0 and where this does not exist. So remember, it's going to be 0 where the numerator equals 0, okay, which is at x equals 0. And then it's also going to not exist, so the derivative is not going to exist when the denominator equals 0, and that's going to happen where x squared minus 4 equals 0. And so here you can see x is going to equal 2 or negative 2. So in this case, these are the critical numbers. So we're going to put those at the points of our intervals, here, here, and here. So we have negative 2, 0, and 2. And our intervals are going to happen in between this. So this is on the entire real number line. So the interval goes infinity up to negative 2, from negative 2 to 0, from 0 to 2, and then from 2 to infinity. Test values, I'm just going to pick negative 3. Here, I'll probably pick negative 1. Here, probably pick 1. And here I'll pick 3. Okay, and again, all we're caring about is the sign. So you can type these into your calculator, and this is about negative 2.3. This one's 0.92. This one here is negative 0.9. And then here, this one's about 2.3. So again, the sign is really what we're looking for. So that one's negative. Here it's positive. Here it's negative. And here it's positive. So that means it's decreasing on this interval, increasing, decreasing, and increasing. And I always just like to draw the picture. So decreasing to increasing, increasing to decreasing, and decreasing to increasing. So this is our min, this is a max, and this is a min right here. Okay, now we just have to do a little bit of work substituting these values back in. So we're going to have a minimum at negative 2 f of negative 2. Negative 2 squared is 4, minus 4 is 0. So this is really at negative 2, 0. We know we're going to have our maximum at 0, f of 0. Okay, so if we plug 0 in here, we get negative 4 to the 2/3, and that comes out to be 2.5. And we know we have another minimum at 2. Okay, and that's going to be 2 squared minus 4. That's 0 again, so 2 comma 0. We get another minimum. Okay, so let's plot these points. Negative 2, 0, 0, 2.5, and 2, 0. And so we know our function here is decreasing. Here we know it's increasing. We've got a maximum. It's decreasing. We've got our minimum. And then it's increasing just like so. Okay, so we've got our mins and our max right here. All right, let's move on. In our next example, we're still doing the same thing. We've got to find the derivative, we've got to find our critical numbers, we've got to test our intervals to determine what's going on. First, when we look at this, we do want to find this derivative. And we can see here that we are going to have a quotient rule. Okay, so it's going to be the low function times the derivative of the high minus the high function times the derivative of the low over the low squared, which is going to be x to the 4th. Okay, so let's go ahead and simplify this here. We're going to get 4x cubed minus 2x to the 5th minus 2x all over x to the 4th. And we can take an x out of all of these. So we get 4x squared minus 2x to the 4th minus 2 over x cubed. And I should probably rewrite this here as negative 2 x to the 4th minus 2x squared plus 1 over x cubed. Okay, now we really want to know where this equals 0 or does not exist. So if we just look at the numerator, where this equals 0 would be where x to the 4th minus 2x squared plus 1 equals 0. And let's go ahead and factor this. So here we see a 4, 2, and a 1. So we can think of this as like x squared squared minus 2 times x squared plus 1. So instead of having an x here, we actually have an x squared. And then, let's see, to get a positive 1 but a negative 2 here, we're going to have to go plus 2 and then minus 1. So we want to know where x squared plus 2 equals 0. Well, that's never, so that's not going to be helpful. We want to know where x squared minus 1 equals 0. So that is going to be at x equals 1 and negative 1. Okay, so we know these are two critical numbers. And we also want to know where the derivative does not exist. And that's going to be where x cubed equals 0. And that's at x equals 0. We also have a critical number here. Okay, so let's go ahead and test our critical numbers and our intervals here. So we have negative 1, 0, and 1. Okay, so the interval here is negative infinity to negative 1. Here it's negative 1 to 0. Here it's 0 to 1. And here it's 1 to infinity. So some test values we could try here. Negative 2. Here we could try 1/2 or negative 1/2. Here we could try 1/2. And here we can try, let's just try 2. Okay, so here, f prime of negative 2, negative 3.75. All I care about is that it's negative. F prime of negative 1/2, that gives me 15. All I care about is that it's positive. F prime of 1/2, that's negative 15. So all I care about is that it's negative. And then f prime of 2 is positive 3.75. And so all I care about is that it's positive. So what this is telling me is that the function is decreasing here. It's increasing here. It's decreasing here. And it's increasing here. Okay, so what that's going to tell me is if we go from decreasing to increasing, that's a min. If we go increasing to decreasing, that's a max. If we go decreasing to increasing, that's our min. So let's go ahead and find those values here. So if I plug negative 1 into my original function, I get negative 1 to the 4th, which is 1, plus 1 is 2, over 1 squared, so that's negative 1 comma 2. If I plug 0 in, I get 0 to the 4th plus 1, that's 1, over 0 squared is 0. What happens? If you plug 0 in, we get a does not exist. Now we remember the first derivative test said that the function actually has to exist here. And if we look, we've already talked about this. If we have an x squared in the denominator, well at 0, we're going to have a vertical asymptote. Okay, so we still needed the 0 because we needed to see what was happening to the function here. But this is not a max or a min. Instead, it's our vertical asymptote. Okay, and then this one we think's a min, and if we plug in 1, then we also get 2 here. Okay, so let's plot in our mins here. We have negative 1 comma 2. We had our vertical asymptote here, and then we have 1 comma 2. And we know this is a minimum because it's decreasing on this interval, and then it's increasing. And then here it's decreasing on this interval, and then it's increasing. So you can kind of see how we got tricked with that vertical asymptote because it was increasing to decreasing, but because the function doesn't even exist there, we know we get that vertical asymptote. All right, so hopefully you feel comfortable with using that first derivative test to find those relative mins and maxes and where the function is decreasing and increasing on an interval. All right, thanks for watching, and we'll see you in class.